Okay, good evening, buenas noches, everybody. Welcome to day one on week 9 of the semester. So last week, before our review, the last topic that we talked about was how to identify organic reactions as either condensation, hydrolysis, oxidations, or reductions, okay? So understand that whenever we have a condensation reaction, in essence, what we have is two different functional groups forming one functional group. And you can see here in the examples that I gave, for example, we have the formation of an ester in letter A. So again, a condensation is when we have two functional groups that come together to make a different functional group at the end. So make sure that you practice with the in-class worksheet. Hydrolysis is a term that we can utilize to describe reactions in which water is cutting molecules. And how do we know if water is cutting a molecule? Because you will see specifically that that water molecule is going to contribute to the product of the reaction, an H and an OH. That's how we know that we have hydrolysis. Next, we have oxidations and reductions. When it comes to oxidations and reductions in organic chemistry, remember, the key thing is to remember the transition of the functional groups. In oxidation reactions, you basically go from alcohols that have to be primary to aldehydes, and then aldehydes to go to carboxylic acids. Or the other reaction is if you have a secondary alcohol, that goes to a ketone. Reductions, on the other hand, is the reverse of oxidation. So for example, if you have a carboxylic acid turning into an alcohol, or you have an aldehyde turning into an alcohol, specifically a primary alcohol, if you have a ketone going to a secondary alcohol, that tells us that we have a reduction. So again, go through the problems in the in-class worksheet in order to practice the classifications of organic reactions. Any questions about this concept of classifying organic reactions? Put a 1 in the chat if you're ready for the next topic. Great. So the last topic that we have when it comes to organic reactions is going to be two different types of organic reactions that specifically utilize unsaturated hydrocarbons as a reactant in the reaction. So as you can see here, we have specifically the reactions of alkenes, okay, which is an unsaturated hydrocarbon because it contains one carbon-carbon double bond, okay? In this class, we don't deal with alkenes that have multiple carbon-carbon double bonds. So understand that an alkene, which is an unsaturated hydrocarbon, is going to contain one carbon-carbon double bond. So when it comes to alkenes can undergo two different types of reactions. The first one is called hydrogenation, okay? So in a hydrogenation, we can see that specifically our alkene is going to react with molecular hydrogen in the presence of any of these catalysts. So you could use this, you know, in terms of the reactants are going to be an alkene is going to be that molecular hydrogen and any of these three catalysts, which you can see is platinum, nickel, or palladium. So the product of this reaction is an alkane. The reason why we call this addition reactions is because overall in our reaction, the carbon-carbon double bond will break, and then in its place, we're going to add a certain atom. In the case of hydrogenation, is going to be hydrogen. So that's why we go from an alkene to an alkane. Hydrogenation reactions is a reaction that I hold very dear to my heart because hydrogenation was my first fire as a chemist, okay? Palladium specifically in carbon, it sparks when exposed to air. So when I was working with it, for some reason, the bottle, a little bit of the palladium on carbon dust came out, and then it sparked. Hydrogen is actually flammable. So when I saw the fire, all I had to do was scream fire. The person next to me took a bucket of sand, threw it inside of the chemical hood, and then we just ran out of the lab. Nothing happened past that, but I learned really quick that when you're handling chemicals, we need to be very careful. So yeah, it happens, you guys. It's one of those things that it marked me for life. And I was like, okay, now I know that I cannot get lazy. I cannot have bad technique. It's very important to do things correctly, read the procedure. You know, you can't feel super comfortable in the lab unless you do something often. So yeah, it was a learning experience really quick. But nevertheless, hey, it makes for a good story when I'm teaching chemistry. Now, the other reaction that we have here, so the other reaction of alkene is a hydration reaction. And when it comes to a hydration reaction, understand that this is where you have an alkene reacting with water, and then you utilize strong acid as your catalyst. Remember that the role of the catalyst is just to increase the rate of the reaction by lowering the activation energy, okay? In the hydration reaction, what we are going to visualize is that specifically our water molecule, as you can see in the bullet points, is going to donate a hydrogen to one of the carbons in the carbon-carbon double bond, and then the other carbon in the carbon-carbon double bond is going to receive the OH. But how do we decide who gets the H and who gets the OH? As you can see in the bullet points, the hydrogen atom goes with the carbon atom in the carbon-carbon double bond that has the most hydrogens. That is directly attached to it. And we're going to do some examples so you guys see. Who gets the OH is going to be the second carbon in the carbon-carbon double bond that has fewer hydrogen atoms directly attached to it. And that's how we decide. So because we have incorporation of an OH, understand that the functional group that we create is an alcohol. Now, one more thing that I want to mention when it comes to hydrogenation specifically. Understand that hydrogenation specifically happens with alkenes, or it can happen with something that has a carbon-carbon triple bond. Let's put in the chat, what is the name of the functional group if it has a carbon-carbon triple bond? Great job, you guys. So alkynes can also undergo hydrogenations. In the case of the alkyne undergoing hydrogenation, we still reacted with molecular hydrogen. But understand that because we have 3 bonds, we're going to break 2 of them. And since we have to add 4 hydrogens, we use 2 moles of molecular hydrogen for alkynes to achieve the alkane. And we are going to use a catalyst. And similar to the alkene, the catalyst could be nickel, it could be platinum, or it could be palladium. Okay? But alkynes can also form alkanes. Now, let's understand, even though we haven't done a lot of naming when it comes to benzene rings, in other words, arene functional groups, that specifically aromatic compounds do not react like alkenes. So under the conditions of hydrogenation or hydration, you are not going to make any changes to arene, okay? So aromatic compounds, in other words, molecules that have arenes, and remember that arenes means that they have a benzene ring. And just to remind you guys how a benzene ring looks like is that hexagon that has alternating double bonds and single bonds. This, we can also write it as a hexagon with a circle in the middle. So it doesn't matter the illustration, they all represent an aromatic compound, which means that that is an arene. So remember, hydrogenations and hydration reactions will not happen to specifically the arenes if you have it as a functional group in your molecule, okay? Put a 2 in the chat if you're ready to practice. Excellent. Let's go through some examples to understand, okay, what kind of reactions are we going to do? In exam 3, you guys are going to need to understand very well how to draw or how to identify the product of a reaction. So please pay close attention. And if you had difficulties in exam 2, understanding, okay, if Dr. Luz gives me a molecule, how do I understand in its skeletal form or in its condensed form? Please come to office hours. I'm more than happy to help you because I observed that in some of those questions in the exam, the percent of students that got those questions correct were lower than in other sections. So I suspect that maybe some of these questions gave students a little bit of difficulty. So if you still have questions about that, please feel free to come to office hours or just send me an email. I am more than happy to provide resources for you to understand these concepts. So first, I want you guys to go through the reactions that we have here, okay? We specifically have 6 of them. I want you guys to first identify which ones are hydrogenation reactions. And let's put the numbers in the chat. Which ones are hydrogenation reactions? From 1 through 6, which ones are hydrogenation reactions? Great. I see number 1. I see number 2. Then number 4 and number 5. Great job, Dominique. Yes, those 4 reactions are hydrogenations. For those students that are like, how does she know that those are hydrogenations? Let's look at the reactions more closely. So look at reactions 1 and 2. We see that we start with an alkene. We are reacting it with H2, and then you see palladium or you see platinum. The other ones could have nickel. So as you can see, oh, I have an alkene, check. That's a functional group. I have molecular hydrogen, check. And then I have these catalysts, palladium or platinum. So when we go to 4 and 5, okay, we see specifically that we have an alkyne, we have an arene, and then we have a number of hydrogen atoms, okay, that are added to them. And in this case, we have nickel as our catalyst, okay? So what is the symbol for the atom that we're adding when we're doing hydrogenations? So what atom in the periodic table are we adding to our compounds if we're doing hydrogenations? Great job on the chat. Exactly, hydrogen. So this reaction is kind of like the Oprah moment of you get a hydrogen and you get a hydrogen and you get a hydrogen and you get a hydrogen. But remember that not all the carbons get hydrogens. Who gets hydrogens? The ones that are double bonded or triple bonded, as long as they are alkenes or alkynes. Understand that arenes do not have that specifically. So let's go through number 1. So what is the functional group that we have on 1 and 2? So what are we reacting under hydrogenation conditions? Alkanes, alkenes, alkynes. What are we reacting? Excellent job. We have alkenes. So this is an alkene and this is an alkene. So in exam 3, when you guys have to predict the product of a reaction, I will be giving you the reaction that you see on number 1. You guys are not going to be submitting structures to me, but from the list of structures that I give you, you guys need to identify how would it look like. So when we look at the molecule that is given to us in this problem, we can see that specifically our carbon-carbon double bond is right here. So what am I going to do? I'm going to predict the product, rewrite this molecule. So I have here a CH3. I have a carbon. I have a CH3. I have a CH. I have a CH2. And then I have a CH3. Notice that I wrote everything except the carbon-carbon double bond. So this is where the carbon-carbon double bond is. Now, because this is called an addition reaction to the atoms that were double bonded, they are no longer going to be double bonded, they're going to be single bonded. Then these two hydrogens that are in molecular hydrogen are going to now be bonded to the atoms that used to be in the carbon-carbon double bond. So as you can see, the product of this reaction, if I rewrite it, this little squiggly line is my symbol for rewriting, looks like this: a CH3 bonded to a CH, bonded to a CH3, bonded to a CH2, bonded to a CH2, bonded to a CH3, and now you can see that we formed an alkane. Questions about number 1? Then let's move on to number 2. We also have an alkene. Okay? This is a haloalkene because you see that we have bromine. So how am I going to identify the molecule that is the product of specifically this reaction? As you can see here, I'm going to redraw my reactant, that alkene, except that I'm not going to include the carbon-carbon double bond. This is where the carbon-carbon double bond used to be, okay? So what are the carbon atoms that were in the carbon-carbon double bond going to get? Hydrogen atoms. So there's a hydrogen right here. There's a hydrogen right here. So understand that if I redraw this molecule and I leave it as a skeletal form, because we are not going to include the carbons and hydrogens, this is how it will look like, okay? Questions on number 2. Then let's move on to number 4. What is the reactant on number 4? What type of hydrocarbon do we have? Let's put it in the chat. Great, that's an alkyne. Great job, you guys. So since we have an alkyne, okay, and let me just write in the carbons and hydrogens for those students that need that. There's a carbon right here, a hydrogen, there's a carbon right here, there's a CH2 right here, there's a CH, there's a CH2, CH3, CH3, okay? So who is going to react here is only these, okay? That's where the hydrogens go. So when I'm trying to predict the product of this reaction, okay, notice that overall in that skeletal structure, I have 1, 2, 3, 4, 5, 6 carbon atoms, okay? And we have a substituent on 4. So understand that when I'm drawing the product, I need to illustrate those 6 carbons, so I cannot drop the carbon. 1, 2, 3, 4, 5, 6. That CH3 is down here, okay? And overall, in this instance, we're going to add 4 hydrogens in the carbon-carbon triple bond. So this carbon, let me actually number it. If this is 1, and this is 2, this is 3, 4, 5, and 6, carbon 1 gets 2 hydrogens. Carbon 2 gets 2 hydrogens. So this is where the carbon-carbon triple bond used to be. So please be careful in exam 3 and also in chapter 5 chapter quiz when it comes to the alkynes undergoing hydrogenation, how the product will look like. So again, each of the carbon atoms in my triple bonds will receive 2 hydrogens. That's why here we have 2 moles of H2. So how does this look like in terms of the skeletal? One, 2, 3, 4, 5, 6. And on carbon 4, we have a methyl. So that's just me rewriting that molecule. Any questions on problem 4? Let's go over problem 5. So what is the functional group on problem 5? Great job, you guys. That's an arene. Now, I mentioned to you guys that when it comes to hydrogenation, arenes are very special, or for that matter, in any type of addition reaction. Can this arene, under regular conditions, react with hydrogenation conditions? Yes or no? Let's put it in the chat. Excellent job. It cannot. So what do we predict when it comes to this? You guys will find within your choices something that says no reaction. Because under normal circumstances for hydrogenation, this is a no-go. Can hydrogenation of arenes happen? Yes, but it has to be under super pressurized conditions. And what I'm illustrating here in this reaction is going to be specifically just normal hydrogenation conditions that we have in the laboratory. So for the purposes of this class, this reaction is going to yield no reaction because, again, this is just regular hydrogenation, and arenes do not react under hydrogenation conditions unless it's pressurized, but we're not going into those details. Any questions on hydrogenation? Since there are no questions on hydrogenations, then let's move on and talk about hydration reactions. And here in the examples that I have, in terms of hydration reactions, we have two examples, number 3 and number 6. Let's first look closely at specifically the hydrogenation that we have on number 3, okay? So I mentioned to you guys a few moments ago that when it comes to hydrogenation, we need water, we need acid, which is a strong acid. Usually when it comes to this, it's going to be illustrated as H plus and H2O. Another way that you could see this is H2O, comma, H2SO4, which H2SO4 is sulfuric acid, and that is a strong acid, okay? So those are the reagents that we can see. Remember that when we have a hydration reaction, overall, what we need to visualize is that our water molecule is going to contribute an H and is going to be contributing an OH, okay? Where? Well, specifically to the carbon-carbon double bond in our reactant, okay? So I'm going to label each of the carbons with a number. Let's say that this is carbon 1 and this is carbon 2, okay? Let's put in the chat, how many hydrogens are attached directly to carbon 1? Let's put it in the chat. How many hydrogens are directly attached to carbon 1? Excellent. So carbon 1 has 1 hydrogen. How many hydrogens are directly attached to carbon 2? Ooh, I agree with Maria. I agree with Dominique and Katie, 0. If we pay close attention to carbon 2, look, you guys, carbon 2 is attached to another carbon here. Carbon 2 is attached to another carbon right here. That's why there's no hydrogens directly attached to it. Put a 1 in the chat if now it makes sense why carbon number 2 does not have any hydrogens. Great. So now that we know that our carbon-carbon double bond on carbon number 1, it has 1 hydrogen, but carbon number 2 has 0 hydrogens. And remember that that is in terms of hydrogens directly attached to them. Then that determines who gets the H and who gets the OH. So when I'm predicting the product of this reaction, I am going to redraw the molecule. This is carbon with hydrogen. This is CH3. This is CH. I'm writing the product already. This is C attached to a CH3. This is a CH. This is a CH3. This is a CH3. This is where the carbon-carbon double bond used to be. This is carbon 1, and this is carbon 2. According to the rules of who is going to get the H and who's going to get the OH, the carbon that has the most hydrogens gets the hydrogen. So that means that this carbon is going to get the hydrogen. What does carbon number 2 get? Carbon number 2 is going to get the OH. So how does the product look if I redraw it? I have a CH2 bonded to a CH3, bonded to a C that has a CH3. There's an OH. There's a CH bonded to a CH3, bonded to a CH3. Okay? And so we continue the labeling because this is the first time we're doing this reaction. Understand that this is where the carbon-carbon double bond was. This is carbon 1 and this is carbon 2. Any questions about number 3? Then let's move on to number 6. Okay, I'm going to give you guys 2 minutes, or let me give you 1 minute because I know that you guys can do this. You guys are capable. I'm going to give you a minute to look at that alkene, and under hydrogenation conditions, I want you guys to predict what will be the structure of the alcohol that we're going to form. Okay, so I'm going to give you guys 1 minute to draw the structure of the alcohol that we are going to form. Okay, let's get started. So the chemistry here, the addition of H and OH, we can establish that is going to happen specifically between these two atoms, okay? And I'm going to label them 1 and 2. So when I draw the product, I'm going to draw the molecule, not including the carbon-carbon double bond. And again, this is carbon 1 and this is carbon 2. Based on the number of hydrogens that are directly attached to either carbon 1 or carbon 2, who gets the H, 1 or 2? Let's put it in the chat. I disagree with all those ones. Thank you, Maria. Let's look more closely at the molecule. If you don't feel comfortable with skeletal structures, just look at them like puppies. Don't be intimidated by organic chemistry. Just see it like this molecule, unless you're afraid of dogs, right? Just be like, oh, this is just a puppy. It's okay. You guys know how to handle these, okay? Or whatever animal you're not afraid of. Just say like, oh, this is just a cute little animal, whatever you're into. Now, when we look at the number of hydrogens, let me identify what carbon number 2 gets the hydrogen. This is a carbon atom that doesn't have any hydrogens because it has a bond, and it has a double bond. So it already has 4 different lines connected to it. So that's why when it comes to identifying how many hydrogens are directly attached to it, carbon number 1 doesn't have any. This is a CH3. This is a CH2. In carbon number 2, there's a carbon atom that is bonded to 1 hydrogen. How do I know that carbon number 2 has 1 hydrogen? Because when we look in the skeletal structure, you guys, carbon number 2 has 1 bond and then the double bond. That's only 3 lines. So that's why the 4th bond is a hydrogen. Put a 1 in the chat if now it makes sense why carbon number 2 has a hydrogen and it gets the incoming hydrogen, okay? So what does carbon number 1 get? Let's put it in the chat. What do we put on carbon number 1? If it's not getting the hydrogen, what's it getting? Great job, the OH. So in the product of my reaction between carbons 1 and 2, understand that specifically number 2 got a hydrogen. If I draw the correct skeletal structure, I don't need to write it in. And then carbon number 1, I'm going to place an OH. Okay? Any questions about hydrogenation or hydration of hydrocarbons, specifically alkenes and alkynes in the case of hydrogenations, or hydrations of alkenes? Great. Since there are no questions, this concludes all the topics that we have for chapter 5. So make sure that when you go through chapter 5 homework, You know how to identify it in all of these problems. Remember that chapter 5 homework is due on Thursday. I have office hours right before class. So if you have any questions about chapter 5, then I'm here to help you. So just make sure that you come to class a little early. So since we finished the concepts of chapter 5, now let's move on to the concepts of chapter 6. So chapter 6 is our chapter where we study carbohydrates, okay? And carbohydrates may be a term that you guys have heard in everyday life, okay? So what are carbohydrates, okay? Now, carbohydrates, understand that are a major source of energy in our diet, okay? Some people avoid them, or they live a low carb diet just because they don't want too many carbohydrates in their diet. Just, you know, they're trying to regulate the intake of carbohydrates, okay? Why are these molecules called carbohydrates? Because the elements that makes them are going to be carbon, hydrogen, and oxygen. So the general chemical formula for many carbohydrates are going to be CnH2O(N). So what does that mean? That understand that they are called carbohydrates because they are hydrated because of the water of carbon. So that's where carbohydrates come from. Now, carbohydrates, one of the reasons why people sometimes avoid them in their diet is because carbohydrates are also known as saccharides, which actually means sugar. And indeed, carbohydrates is a source of sugar in your diet. Now, carbohydrates can be found in a wide array of foods and compounds that you may be, you know, familiar with from your diet. As you can see in the image that we have on the left side, we have potatoes, we have pasta, we have rice, we have beans. All of these are sources of carbohydrates that may come from our diets. Now, it is important to establish that when it comes to carbohydrates, plants specifically are able to make carbohydrates. And you can see here that plants specifically, via the reaction of photosynthesis, can take carbon dioxide, water, and they take energy from the sun, and via photosynthesis, they can make a carbohydrate. And for example, here I'm illustrating that they can make glucose, okay? When it comes to us, there is a wide array of biochemical pathways that we're going to learn in chapter 12, in which explain how in our bodies, it's not that we're going to utilize CO2, water, and energy. How we synthesize carbohydrates is going to be different. It's different biochemical pathways that are utilized, and it depends on the need for the body. Now, can we use carbohydrates? Of course. So whenever we consume carbohydrates, understand that in our bodies, through the process of respiration, we can take a carbohydrate and convert it into CO2, water, and energy. So as you can see, we can take that molecule that has carbon, hydrogen, and oxygen, and we are going to react it with molecular oxygen to make CO2, water, and energy, okay? So let me post a question to you guys. So what type of reaction is respiration? What I mean by this, earlier we learned, and that was in the test, different types of reactions, okay? Combination, decompositions, single replacement, double replacements, all that kind of stuff, and combustions also. What type of reaction is respiration out of the 5? What kind of reaction? Let's put it in the chat. When we have a molecule reacting with O2, making CO2, water, and energy. Thank you, guys. Exactly. Look at how beautiful the human body is. I'm telling you, nature is the best chemist. Best. This is why research is so interesting. And even though I used to do it, I'd rather be teaching, to be honest with you. But it is so amazing to understand that our body actually combusts carbohydrates, but we do not explode, okay? So every time you're consuming carbohydrates and other nutrients, understand that the body, specifically I'm illustrating carbohydrates, it is a controlled combustion. Energy, as we're going to see later when we study biochemistry more in detail, we're going to see how we develop these molecules that upon hydrolysis are going to release chemical energy. But I just wanted to illustrate that this is just amazing. When you eat and you are burning those carbohydrates through the process of respiration, all you're doing at the end of the day is a combustion reaction. Now, let's learn the different classes of carbohydrates that you guys need to be familiar with in this course. When it comes to the classes of carbohydrates, there's going to be 3 main classes of carbohydrates that you guys need to know, starting with monosaccharides. So monosaccharides are going to be the simplest carbohydrates because they only have 1 unit of sugar. So you guys can see here different examples for monosaccharides. We have glucose, we have fructose, we have galactose. There's actually many more monosaccharides from this. There's actually mannose, there's actually fucose, but anyways, I just decided to give you guys the most common monosaccharides that we know are present in many of the examples from nature: glucose, fructose, and galactose. And we're going to talk about them in detail later in the chapter. Then we have disaccharides. When it comes to a disaccharides, like the name says, the prefix di, which we have learned previously in chapter 4, when we learned to name organic compounds, we know that di represents 2. So that's why disaccharides consist of 2 monosaccharides. And we can see here examples of disaccharides. There is sucrose, and understand that sucrose, this is what we know as table sugar. There is lactose, and lactose is what we know as milk sugar. And then we also have maltose, and maltose is what we know as malt sugar. And you can see here the different monosaccharides that when they are linked together, they make this disaccharide. Lastly, we have polysaccharides, and polysaccharides are going to be polymers, meaning chains of monosaccharides that are long. And there are different polysaccharides that we're going to learn about in this class, but to give you guys an example of one, here we have the example of starch. Starch is one of those polysaccharides that can be found in many food products, including potatoes. They are very starchy. Bananas are very starchy. Now, understand that when it comes to starch, starch is a source of glucose, because these red dots that you see in the molecule of starch are representing glucose molecules that are linked together. In this course, when it comes to polysaccharides, we are only going to be learning about polysaccharides that are made out of glucose, okay? Now, Let's talk about the functional groups that are present in monosaccharides, okay? So here we have the example of glucose and fructose, okay? So utilizing the chat, I want you guys to identify what are the two main functional groups that we find in glucose. Let's put it in the chat. The main two functional groups that we find in glucose. I agree with the alcohol. So as you can see, we have many of them. So I agree with the alcohol. Those are alcohols. What is this? That's not an ester. Thank you, Dominique. Yes. That is an aldehyde. Oh, right here. It's an aldehyde. Now we can observe that fructose has a similarity to glucose, okay? We can see that the alcohols are present. OH, 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 okay? But let me highlight a difference. What is the functional group that is a carbonyl that is bonded to carbon chains on either side? So what I highlighted in blue, what is that functional group that I highlighted in blue? Excellent. That is a ketone. So let's understand that when it comes, as you can see in the bullet point, monosaccharides contain several functional groups. And you can see that we have alcohols and we highlighted them. They have aldehydes and they also have ketones. Now, understand that when it comes to naming these functional groups, they are not specifically giving you the rules for naming alcohols, aldehydes, and ketones in the textbook, but in the slides, I actually gave you guys the rules for naming aldehydes and ketones and also alcohols. So I want to just take a moment and at least teach you guys how to name alcohols, aldehydes, and ketones. So for those of you that in your future studies, or you may have to take the TEAS exam, I want you guys to have at least that under your belt. Let's first deal with the alcohols, okay? When we are naming an alcohol, we're going to find the longest carbon chain, okay? We're going to write the alkane name, and then in the alkane name, we're going to replace the E ending with OL because we're naming an alcohol. We're going to number the chain starting from the end that is closest, okay, to the carbon that has the OH, and make sure that you don't forget, oh, instead of chapter 11, this is going to be chapter 4 for you guys. Don't forget the rules for the substituents that we learned specifically in chapter 4. Okay? So I think we will have time to at least learn how to name alcohols. Let's put in the chat, what is the number of carbons in the longest carbon chain that we have in this particular alcohol? Let's put the number. How many carbons do we have in the longest carbon chain? Great job, you guys. Excellent. So there are 6 carbons, which are right here. okay? So if we have 6 carbons in a row, what is the alkane name for that? Great. Hexane. Now, because we have an alcohol, we are going to erase the E ending, and we're going to put OL. So this is going to become hexanol. Now, when we have an alcohol, we need to number the parent chain, starting from the end that is closest to the OH. So do we start at the right or do we start at the left? Let's put it in the chat. Great, we start at the right. So for this, we're going to do 1, 2, 3, 4, 5, 6. Now, for alcohols, we need to number the carbon that is holding the OH, okay? Which in this case is going to be carbon number 2. So the 2 in front of hexanol lets me know where the OH is sitting. In this molecule, we have 1 substituent. So that substituent is sitting on carbon 5. So what will be the prefix that we put before the 2-hexanol? Let's put it in the chat. Great job, you guys. 5-methyl. So as you can see, the name of this molecule is going to be 5-methyl 2-hexanol, okay? So when we come back on Thursday, we are going to continue naming the alcohols, the aldehydes, and the ketones, and then we're going to proceed talking about carbohydrates a little bit more. Thank you guys for coming. Have a good night.